Hi, welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore, your co host.
So, we're broadcasting live from the campus of the University of North Dakota. If you have any questions during the live podcast, feel free to send us a chat, and we'll be checking that throughout the podcast. So, please don't be shy. Also, if you finish watching the podcast, you enjoy what you see, don't hesitate, please, to give us a thumb up and like it, or even subscribe to our channel. So, Robert, one of the things we always talk about on this podcast, it seems, at the very beginning, is always related to the weather.
Right.
What do you think about our weather?
I think it's pretty cool right now. It's mostly sunny out there and everything. Oh, wait, there's a nice smoke haze out there today. So if y'all hear me coughing a little more than usual, you know what it's caused by.
Right. Well, it's that time of the year, I guess, where
Yeah.
that seems to be quite normal in some sense. Every summer, there's at least a few days that we get where it's quite smoky. And one of the interesting things when we see the smoke in the atmosphere is the effect of the light passing through the atmosphere is really dramatically illustrated.
It is.
And one of the things we notice is, for example, is the sun is really red even throughout the middle of the day. And that's just an illustration, of course, the smoke particles are of the right average size, that they block a lot of that short wavelength light, even more so that gets scattered and absorbed on a normal day when we don't have all that forest fire smoke.
The long wavelength goes through it, the short wave gets stopped by it.
I mean, that's the explanation why we have a blue sky, right? So as a young child, you would ask, why is the sky blue? Why isn't it like green or purple or something like that? And the answer to that is the fact that the atoms and the molecules and the dust particles that make up our atmosphere are of the right size compared to the wavelength of optical light that we get from the sun. That it is the blue photons that get scattered more so than the other longer wavelength photons in the optical. And so therefore those blue photons coming from our sun are scattered all over the place. Eventually they enter your eye. And so my blue sky is unique in the sense it's those blue photons that I see as the blue sky where you have your own blue photons that enter your eye.
Right.
So in that sense, we see different skies, if you want to think of it that way.
Well, for a future podcast, at least for a momentary slide, I'll point out this by asking you the question, what color is the atmosphere really?
I know you're getting at something here, so I'm not going to say, what is it, Robert?
For the most part, it's black. And the reason is because our atmosphere actually absorbs almost all the X-ray and UV that come in. And it absorbs a great deal of the microwave and radio. So there's really only a very small window from what we call the optical wavelengths that get through. So there's these narrow windows in the optical, the infrared that get through the atmosphere. Everything else is absorbed.
Right.
So
yeah, I mean, it really illustrates the point with the smoky sky, the fact that the sun looks red, and you could compare it to what the sun looks like at dawn and dusk.
Right.
You get the red, and so the light is passing through more of the atmosphere than it is at local noon. And so you get more of the shorter wavelength light gets scattered and absorbed, leaving you with just the longer wavelengths that get through to your eye. And therefore you get the perception of that orange sky or the orange sun when you look at it.
Yep. And I'll try to remember, and I'll bring up a slide, one of the future shows that shows that wavelength, the windows through the atmosphere that bring it up, because it's a real interesting thing to see what gets through the atmosphere and what doesn't.
Yeah, so that really emphasizes why it's important, if you can afford it, to get our telescopes into space.
Right.
It really, really makes a big difference on what we see,
Right.
what we can detect.
The blue sky thing, you got to remember, that's happening even at night. The blue photons that try to get through the atmosphere are scattered all over the place.
Well, remember that the sun is below the horizon, so the source of those blue photons
Is your star your target?
That's
your
right.
planet,
It's
and so
right.
forth.
It's just not the sun.
Right.
Right.
But yeah, the blue is being scattered everywhere, so more of the red gets directly through the telescope.
Right. So if you were to measure the color of the stars very, very precisely with a telescope that's in orbit around the Earth, above the atmosphere, and then compare that same type of measurement with stars that you see from the ground, you'll notice a shift in color.
you will see a shift in color.
And we're just referring to the optical. We're not talking about other wavelengths beyond the optical.
Yep.
And so there is a perceived color shift because of our atmosphere.
And it has to be taken into account when you're doing scientific work with this stuff.
That's right. And then the other thing is, and you can imagine why. Well, imagine your life form that lives on a different planet that had a different type of atmosphere, and it has this different effect to the light that you receive at different wavelengths, let's say in the optical, in other words, the color of a star.
Yep.
Then your colors are not going to be the same as what somebody would measure on the Earth because you're looking through a different type of atmosphere. So you really need to correct for that and say, what would be the color of the stars if I wasn't looking through an atmosphere at all?
Mm-hmm.
So that's the type of correction that one needs to make.
And it's nifty how they do that and everything. I mean, it's a process, though.
And even then, there's another sort of correction, since we're talking about the color of stars, is the fact that there's interstellar dust within our own galaxy and in other galaxies as well, but we're looking at stars in our galaxy, and there can be a certain amount of dust, and it depends exactly where you're looking. In some locations, there's a lot more dust in the way, if you like, that is between us and that star that you're looking at. And so when you look through the dust, it does the same kind of effect that you see here with the smoke in the Earth. It makes the stars look redder. So we call that interstellar reddening.
Yep.
So it's a shift towards the red side in the color of stars. And if you want to know the exact property or the color of a star, the intrinsic property, without that interstellar dust being in the way, then you need to correct for that reddening effect.
Yep.
And that's...
And it is possible to model it and get rid of it. It's a thing, it's a process, but you can do it.
Yeah, and the other thing is, I mean, the interstellar dust is not smoothly distributed evenly all through the whole galaxy. It's patchy is one way to think about it. And so therefore, there's a lot more dust if you look along the plane of our galaxy than it is if you look perpendicular, that is opposite the plane, let's say 90 above or below, if you wanted to visualize it that way. And so you need to make those type of corrections.
And that's the type of thing you actually do to go into those corrections, is you look at things out of the plane that are the same type of thing, and then you look in the direction you want to go and how much redder does it look and things like that.
Right, and if you want to think about what is the amount of correction that you need to make, we know it's directionally dependent. Like I said, some directions there's a lot more dust in the way for a certain distance than it is in other directions. And so you need to really map out where's that dust, where's the interstellar matter. And one way to do it is to make observations in the infrared, because we know if you heat up dust, if dust absorbs radiation, like the background field of light that's coming from stars, that dust is heated up to a certain temperature depending on where the dust is and so on and so forth. But the thing is that when that dust gets heated up, it has to get rid of that gained energy, and it does so by emitting mostly at infrared wavelengths.
Right.
Which means which type of telescope do you need to use to map out the distribution of dust?
An infrared telescope.
An infrared telescope.
Which is, don't we have one up in space right now?
Yeah, well, James Webb would be the best one, but we've had lots of
Sorry,
reasonable telescopes like the Spitzer Space Telescope,
which was a good instrument.
the Herschel Space Telescope, and even previous generation type of infrared telescopes. And so they have mapped out the distribution of that dust, which gives us a better idea of how much dust lies between us and some distant target. And there are other things you can do besides that, but that's just one line of avenue that you can go down.
I will point out, because we've shown the pictures here, that's why those pictures of the central black hole in the Milky Way are in radio wavelengths, because the longer the wavelength, the less it's disrupted by that dust. So radio wavelengths being the longest, if you want to see through the gas and dust that's between us and the center of the Milky Way, you have to look in radio wavelengths. You really do.
Yeah, and it's interesting you mentioned that. There was a study, it came out, I think, a couple of weeks ago, but it recently appeared, I think, even this morning. And the report was a study that a team had done looking at the structure of the Milky Way. And there were ideas or suggestions that the Milky Way contained 4 main spiral arms. And this latest study suggested there are actually only 2 that come, the starting point, emanate from the end of the bar. The end of the bar that's in our galaxy.
Right.
So we knew for several decades now that we live in a barred spiral galaxy. And it's very difficult to see what's happening at the ends of the bars, to see if there are just 2 spiral arms.
Because they're dust.
Because of the dust is in the way, the interstellar matter. If you're looking towards, And the bar is not side on to us, it's pointed a little bit towards us, not directly, but a little bit. And so in either case, you're looking towards the bulge area of our galaxy, towards the center region, and there is just a lot of interstellar matter in the bulge of the Milky Way. And that hinders your view in the optical. So you really need to go to infrared or even longer, like in radio.
Radio, microwave, and radio.
And so the suggestion now is that there's hints that there's actually only two main spiral arms to the Milky Way, each of them starting at the end of the bar. And we see that in other galaxies. That's not unusual. Other barred spiral galaxies have, usually two main spiral arms that start at the end of the bars and spiral outwards type of thing. And so, it's interesting, chances are maybe that's the case. It wouldn't be surprising if
It's another example of, as we learn more, we refine what our views of things look like.
Right, and a lot of that learning more means developing of technology, improving our telescopes in terms of sensitivity, doing larger surveys that go much deeper, or looking at fainter sources. All of these things have a dramatic impact on the advancement of astronomy and astrophysics.
Absolutely. So things will keep changing, folks.
And to kind of go down that rabbit hole of what the impact is of advanced technology, then with our our knowledge of what we have in astronomy, as the universe as a whole, one of the things that had come up just recently last week was looking at what we call the Hubble tension.
Right.
So if we want to look at the first slide, Robert, we'll
Certainly.
illustrate that point. So what is the Hubble tension? So the Hubble tension really has its, if you like, origin a few years ago, when people started to come up with methods and techniques that could measure very precisely, at least compared to what they could do, a couple decades before this time period. So this would be like in the late 1990s, the early 2000s, measure very, very precisely the expansion rate of the universe itself, the so-called Hubble constant. Okay. Now, I remember like way back, this would have been like in the 1980s, let's say, we thought the Hubble constant was somewhere between 50, and the units for measuring the Hubble constant are typically in kilometers per second per megaparsec. And I'll explain those units in a second. Somewhere between 50 and 100.
Right.
So there's a factor of 2, uncertainty in the expansion rate of the universe. And so the units there, the kilometers per second per megaparsec, the kilometers per second is a measurement of velocity or speed. Right? We're not telling any directional information here, so it's a speed. And then megaparsec is a unit of length. Now, we've mentioned this before, but just to summarize in case you've never listened to any of the podcasts prior to this one, a parsec is a unit of length. Right. It's defined at what is the distance that a star would be from us, from the Earth, such that it would display a parallax of 1 arc second. And a parallax is the shift in the apparent position of a nearby object relative to background objects, objects further away, when you change your vantage point of observing. So imagine, this is the technique of surveying. For example, if you wanted to come up with what is the distance between some location to a tree that lies on the other side of a lake, and you have, you don't want to travel around the lake to try to kind of measure that. You could do it by trigonometry. You could measure the positioning of the tree on the other side of the lake relative to background trees that are much further in the distance, and then change your vantage point. So move your surveying equipment to somewhere else, let's say, 50 feet away on the same side of the lake, so you don't have to cross the lake or travel all the way around it, and look at that same tree. And then note that the angle, where that tree looks like relative to the background trees, has changed, and you can measure that angular shift in position, and that's related both to the distance to the tree and the distance between your 2 points of observation, what we call the baseline or the separation of those two locations.
And I'll just throw in, you can get a feeling for this by holding your finger up at arm's length and closing one eye and then the other, and you can see that your position of your finger seems to shift between the two eyes against the background.
Right, and you can actually even notice that if you put your finger, let's say, fairly close to your nose and looked at the position of your finger relative to the background, first looking with one eye and then the other, and then move your finger out as far as you can get it and repeat that process, you'll notice the shift is a lot smaller when the distance to your finger is the greatest. So that just tells you that the further away an object is, if you don't change your length of your baseline, the smaller will be the shift in the position of that object from the two vantage points. And so we can use that parallax technique, as it's called in astronomy, to measure the distances to nearby stars.
Right.
And a parallax is defined that if that shift, and actually it's half of the total shift, if the half of the total shift is 1 arc second, then the distance to that object is about 3.26 light years, and we call that 1 parallax second, or 1 parsec for short.
Yep.
Now, and when you talk about 1 arc second angular measurements, think of a circle, go around once in a circle, that's 360 degrees. You divide that into 360 equal angular slices, that's 1 degree. You divide that into 60 even angular pieces, that's 1 arc minute, and divide that 1 arc minute into 60 even pieces, and that's 1 arc second. So it's a very, 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 very tiny angle that you're measuring. So if a star was located exactly 1 parsec away, it would shift in position when you observe that star from opposite side of the Earth's orbit. That's the baseline, the diameter of Earth's orbit. Okay. So then when you use that technique, you might say, okay, if a distance to an object is, let's say, 3 times that length, then that would be 3 parsecs. If it's 1,000, we call that 1,000 parsecs, or a kiloparsec. If you had 1 million parsecs, that's referred to as 1 megaparsec. And because in cosmology we're measuring distances over vast length scales throughout our universe, we easily can get to mega parsec, literally, billions of parsecs even.
Right.
So when we talk about the expansion rate of the universe, it's usually set up that we measure how fast something is moving away from us. Think of a galaxy and its recessional velocity. We talked about that in the last podcast. Those speed measurements are measured in kilometers per second.
Right.
And because the universe is expanding at a certain amount for every standard length of space, like a megaparsec, then you can write down the expansion rate in terms of so many kilometers per second for every megaparsec. So for example, let's say the expansion rate, or the Hubble constant, is 70 kilometers per second per megaparsec. What that means in practice, because that's a measurement of the expansion rate, it just means for every length of space, that's exactly 1 megaparsec in length, which would be 3.26 million light years in length, that amount of space is getting larger by 70 kilometers as every second goes by on the clock.
Right.
That's the expansion rate of the universe. As I mentioned, a couple decades ago, people thought that number was anywhere between 50 kilometers per second per megaparsec, upwards to about 100 kilometers per second per megaparsec. But those techniques that we use to measure that expansion rate had been refined and made more precise over the last couple decades, to the point now where we can actually measure that expansion rate within a few percent. As far as we know, that is, few percent being the uncertainty, the total uncertainty of our measurements.
Right.
So people are, one of the things that have developed in the last several years is that there's been sort of 2 camps of the expansion rate. And we'll show you a slide in a second to illustrate that. So maybe we should go there now if you want to go to slide number 2, Robert, please.
Yep. Like that.
Yeah, and so what you're seeing here then is a clumping of 2 measurements. So if you just concentrate on the top of the slide, the top panel, one of them involves looking over very large distance scales, essentially the size of the universe. And this is through the measurement of the leftover heat from the Big Bang, the cosmic microwave background. So this was done most precisely by the last greatest or newest generation of satellite that we put in space, a telescope essentially, that measures the leftover heat from the Big Bang and sort of then microwave regions of the electromagnetic spectra. And that mission was launched by the European Space Agency and is known as the Planck satellite. And so the Planck measurement, which was released, the final measurement of several years of accumulated data, the measurement was released in 2018. So that's relatively new. And they came up with a measurement of the expansion rate of the universe on the order of about 67.4 kilometers per second per megaparsec. And the uncertainty on that is relatively small. It's on the order of just a couple percent or so. Now, in addition to that type of measurement, there have been other measurements that have been done, and these use, for example, supernova type 1a to measure distances independently to different galaxies. How does that work? Well, first of all, a supernova type 1a is the progenitor is a white dwarf that have accumulated enough mass that it exceeds the 1.4 times the mass of their sun limit. And that's Chandrasekhar mass limit. And so a white dwarf is mainly made up of carbon and some oxygen. It's the end state of a low mass star in terms of its evolution. In fact, our sun will turn into a white dwarf in approximately 6 or so billion years from now. Okay? And so if these white dwarfs can accumulate enough mass, maybe from a nearby companion star, and that companion star has a smaller mass than what turned into a white dwarf, and if you have a smaller mass, then it takes longer for you to go through all your evolutionary cycles. So you could have a situation where one star has evolved to become a white dwarf, and a nearby companion star is just leaving the main sequence now, expanding out, becoming a red giant. And if the outer envelope of that red giant gets too close to the white dwarf can actually pull that material towards itself. That is, the gravity from the white dwarf is stronger than the host gravity of the red giant. And so that outer material can fall on top of the white dwarf. And if that white dwarf can accumulate enough mass to exceed that 1.4 times the mass of the sun, the Chandrasekhar limit, then it will explode as what we call these carbon detonation supernovae. Mm-hmm. Now, because, and it's known as a type 1a to be technical, but because these supernovae, these particular type, these carbon detonation supernovae, all come from the same type of beast, the progenitor being the white dwarf that just exceeds 1.4 solar masses, when that star blows up and reaches a peak brightness, that peak brightness can be calibrated. So we know what the luminosity is. That is, like, think of a light bulb, we know the wattage of the light bulb. Right. Now we know that when light is emitted, I should say, from a star in all different directions, that light falls off as 1 over the distance squared. So it's not like a laser wouldn't do that, because laser light is collimated, not emitted in all different directions, like an incandescent light bulb or something.
It's emitted in one direction.
That's right. So the light from a star then falls off as 1 over the distance squared. So if you know the peak brightness in terms of its wattage or luminosity, you just have to compare that to what is the peak brightness that you measure in usually some faint type 1a supernovae in some distant galaxy. And by comparing those peak brightnesses, one is the apparent brightness, one is the intrinsic brightness from the luminosity, then they are related via the distance.
1 over d squared.
So we have a way of measuring the distances then to these type 1a supernovae.
Right.
And so when people use those type of measurements to measure the expansion rate of the universe, they find values of this expansion on the order of 73 or so kilometers per second per megaparsec. And one would say, okay, 73 is pretty close to 67, 68. They're not off by that much. I mean, in fact, you just go back in history 20 years or so, and it was between 50 and 100. They're a lot closer than that. So what number would you use, back in the 1980s? You'd say it's 75 plus or minus 25 kilometers per second per megaparsec. You go right in the middle if you liked, right?
Right.
Or you go to one extreme or the other. The important thing is you just let people know which value you're using. Yeah, right. Exactly. So here we have two values that are relatively close together, but because we think the uncertainties, and we can get into a whole podcast of explaining the different types of uncertainties. There's random uncertainties, there are systematic uncertainties, and just to say the difference of the two, imagine you're measuring the length of your table in front of you, if you have one in front of you, and you're measuring it with a ruler, and you measure it, 25 times or so. And then you average that number together to say, okay, this is the length of the table plus or minus some uncertainty.
Right.
But let's say that the way you measured it with your ruler was that your head, instead of looking directly down and reading the numbers at the end of the table, you were always slanted, let's say 45 degrees. So you came in on an angle. So you consistently measured, let's say, the length of the table to be shorter than what it actually is. That would be a systematic type of uncertainty or error in your measurement. So anyway, so the issue here is that even though the numbers are fairly close together, 67 versus 73, the uncertainty on these numbers are so small that they differ by a value that's on the order of 5 times the uncertainty, what we call in science a 5 sigma difference.
So basically that top part of this figure tells the story. The green and the blue do not overlap. And so you've got the uncertainty for one method and the uncertainty in the other one. And the ideal situation would be that there's some overlap between their uncertainties. In this case, we don't have that.
We don't have that. And so if you accept the idea that the uncertainties are well established, and that can be a question mark, and of course people look into this stuff trying to figure out what's going on. If it's well established so that the uncertainties are as plotted here, then there's something wrong with the measurement of the expansion rate of the universe, in the sense that if you use the cosmic microwave background measurement, you get an expansion rate that is lower than what you get by using more local methods and techniques, like using supernova 1A, using Cepheid variable stars, and there are lots of other techniques that people use that we don't have time to really go into, all the different techniques. So you get these two discrepant values. That's what's referred to as the Hubble tension. It's a Hubble constant, it's a tension because they don't overlap and their values.
And so we're left wondering which one is the right method.
Right. So it's been interesting that for the last several years, since 2018 essentially, the most measurements that I'm aware of have always come in the higher value of the Hubble constant, in the 70s.
Right.
There haven't been any that came along, to be agreed with the Planck measurement. There's been a couple, but let's say the vast majority have been, in the 70 ballpark range, and more consistent with those local type of measurements. And why they're called local is just the fact that they're using galaxies that are relatively nearby. Remember, the Planck measurement from 2018 is using the whole universe. It's measuring the leftover heat from the Big Bang that's spread throughout the whole universe, the cosmic microwave background. And so in that sense, it gives you a universal measurement, where the value that comes in the 70s is more local in that sense, right? But local is pretty far, right? We're not talking about the Earth local.
I mean, until James Webb, we pretty much were limited to things that we could some other way get the distance so that we could check the type 1A distance, and how far away can you see the type 1A, and all of that sort of thing. So yeah.
So the nearby measurements then, if you want to think of it in that terms, provide you a faster expansion rate than the distant measurements.
Right.
That's what seems to be happening here. Now you might wonder, and if you first think about it and look at the distribution of galaxies, so if we can go to slide number 3, Robert.
Okay.
What this slide illustrates is the fact that, and this is an illustration of what we call the large-scale structure. So think of the distribution of galaxies spread throughout our universe. If one were to ask you, how are galaxies distributed through the universe? Maybe an answer would be they're randomly distributed, that there's no structure to the distribution of galaxies.
Olber's paradox.
Now, it turns out that's not actually true. When we first started measuring, real good measurements were done in the 1980s with the Center for Astrophysics redshift survey. What we discovered is that galaxies are not distributed randomly. They're structured to the distribution of galaxies. They form these giant bubble-like things, or filaments, or walls and sheets and so on. We also see areas, and as illustrated in this slide, that has an underdensity of galaxies. They have a low density. We call these voids. So these regions, typically could have densities only 1/10 of what we find in the walls of the bubbles, the outside that defines the voids themselves, and the filamentary-like structure. So you could think of the distribution of galaxies in the universe as like a giant 3-dimensional spider web. In fact, we call it the cosmic web. And along the threads of the webs where you find the highest density of galaxies, and where the threads cross each other, those are the nodes. Those are where we find the galaxy clusters and so on. And in between the spacing of the web itself, the threads of the web, the empty areas, when you think of a spider web, that's where we have the voids. Mm-hmm. And so you wonder, well, then where are we located? Well, on this diagram illustrates where we're located. So this was a study that was done by Brett Tully from the University of Hawaii. And what it indicates is that the Milky Way itself is actually near the edge of what we call the local void. It's the void closest to our location. So the Milky Way is part of the local group of galaxies. That includes the Andromeda Galaxy, M33, and some other satellite galaxies and so on. We are situated with what we call the local supercluster, At the center of it is the Virgo cluster of galaxies. So if you look near the center of this this picture that's drawing here, you see Virgo. That's the position of the Virgo cluster of galaxies. Notice the Milky Way is on the outskirts. We're roughly about 60 million light years from the center of the Virgo cluster of galaxies. So we're not part of that. We're in a galaxy group. But that whole structure, including us, as well as the Virgo and some other galaxy groups that are around, we call that the local supercluster. But beside us is that local void, as labeled in this diagram. And so if we're at the edge of a void,
Right.
one could make the assumption, because the density of matter is low around us because of that local void, that would impart an artificial higher value of the expansion rate of the universe. So we're affected by large-scale structure, stuff that's local around us. But if you're looking at, that would give you a larger value than for the Hubble constant, maybe a value in the 70s.
Because, correct me if I'm wrong, but the Hubble constant is affected by the local density of matter.
Yeah, it's affected by the density of things. And if when you measure the cosmic microwave background, you're measuring over such a large region of space, the universe, that you're averaging over, hundreds to thousands of these voids. So the effect of the local void gets washed out. It's negligible.
Right.
And because of that, that gives you a lower value of the Hubble constant. So that would explain why you have the so-called Hubble tension. But of course, this suggestion is an obvious one. You don't need Einstein to make this suggestion. And it had been suggested in the past. And some people have gone out and measured this, and they said that the effect of the local void, it doesn't make the difference. It's a 1 sigma type of effect. It's not enough to make up the 5 sigma difference between what you get from the CMB measurement and what you get from using supernovae and Cepheid variable stars.
Interesting.
Yeah. So they claim, at least one study that I looked at, claimed that the effect is negligible in that sense. There's something else going on here. Now, the interesting thing that happened late last week was the publication of a new study. It actually came in the form of 2 papers. So, Robert, do you want to go back to slide number 1, please?
Absolutely.
And this was using the lensing of a supernova and looking at the delay times due to the fact that the light coming from the supernova passes through the space of a foreground galaxy cluster. So on this is data taken with the Hubble Space Telescope. Okay, the study's done by Patrick Kelly. By the way, Patrick Kelly was actually here a couple of years ago, gave a colloquium on his results from just a couple of years ago. That's part of this study. So in some sense, this is a follow-up of what's been happening since. And what's going on is that you can see a galaxy. So if you look in the insert that's in the upper right, it says Spring 2016 imaging. What's labeled there as S1, S2, S3, S4 is the image of a supernova that went off. And because the light has taken different paths because of the highly curved nature of the space that lies between us in that galaxy that contains that supernova, the supernova actually appears in different regions.
Mm-hmm. Okay? Einstein rings.
It's Einstein rings type effect, that's right. And by doing precise modeling, Kelly and his collaborators were able to predict when you'd see an appearance of the supernova explosion in a different part of the image of the galaxy, based on the modeling of the mass distribution that's causing the warpage of space due to this galaxy cluster that's in the foreground. So they made a prediction on when the supernova should appear and at what location. And this is what you see from the 2016 imaging data in that insert in the upper right. You see reappearance, and it's labeled SX. So that supernova reappeared. In fact, there was one that should have been in the SY position, which is sort of in the top left of the image here, labeled late 1990s, but nobody was looking at the time. It was missed. That's the label SY.
Oh, that's unfortunate.
Yeah, and so they were able to get follow-up HST images to look for the appearance of the supernova in 2016. If you put all this information together, what you're seeing is images of the supernova over the span of several years at different locations. And why it appears at different locations, separated by time of years, is the fact that the light is taking paths that have different lengths. And obviously light, since it travels at a finite speed, about 300,000 kilometers per second, when light goes through a long path, it takes longer for the light to reach us. So it's delayed by a certain period of time, that period of time meaning, of course, what is the length, path length that light needs to take.
Right.
And by very precise modeling, the researchers were able to therefore measure these light delays from the imaging, compare it to the modeling, and from the modeling come up with an estimate of the expansion rate of the universe, the Hubble constant.
I would not have wanted to have to do that math.
Yeah, so this is independent of the cosmic microwave background. This is independent of the supernova 1A measurement because we're just looking for the appearance of a supernova and looking at the time delay. So it has nothing to do with the event itself. So you could use a different type of supernova, like a type 2, a massive star that core collapses. You can use that. It has nothing to do with Cepheid stars in that sense, of measuring directly the distance to these galaxies from that technique. So this is a new independent way of measuring. Now, what type of value do you think they got for the Hubble's constant?
I'm figuring probably around 70.
No, they got about 67 kilometers per second per megaparsec. Here is the real good study that's been done, really, really detailed, of measuring the expansion rate of the universe, and it puts the value consistent with that which was measured by the cosmic microwave background.
Well, that still leaves me with the question then, why do all the other measurements give in the 70s?
That is the question. Now, what's the answer to it? Well, right now we don't know. It could be there's something that we're just missing.
Right.
That's appears in all of these more local studies, some systematic offset that we don't know or realize about. That's a possibility. Other people have suggested before this study was announced that involved these time delay of the supernova measurements, that maybe the early universe is affected. So people have invoked this early dark energy. So we talked about dark energy at length last podcast. And so maybe there was another part of dark energy that sort of reared its head early on in the history of the universe. And that kind of faded after a while. Its contribution to the overall expansion history of the universe then went away, and you're left with this cosmological constant, this constant low value dark energy that we see today, that we measure today. Right. Maybe so there's something going on in the early part of the universe that would give rise to this lower value of the expansion rate based on the cosmic microwave background. The thing to note is when we measure the CMB, we're measuring the condition of the universe as it was approximately 380,000 years after the creation of our universe, the Big Bang. Right. That's what we're measuring. So if something happened in addition to what the standard Big Bang, something happened in the early universe, then that would have an effect on what we measure. It could have an effect on what we measure in terms of that expansion rate that depends on the cosmic microwave background. It depends on what the universe was like 380,000 years after the Big Bang. And if that something went away because maybe it was decreasing, and the idea of this early dark energy is that the energy density dropped off faster than the radiation density, so that today it's essentially negligible, or has been negligible for most of the history of the universe. Right. Then it won't affect any of our measurements that we have around today. It will only affect things very early in the history of the universe, including this type of measurement that we're talking about here, the CMB measurement versus the more local measurements. So that's one hypothesis. We don't know if that's the case. That's one idea. And so the theorists are busy trying to explain the so-called Hubble tension, and we just don't know, of course, the resolution of it.
Join us and go win your Nobel Prize.
There you go. So that is one of these issues in astronomy now that's kind of at the forefront. It's certainly in cosmology. In fact, it affects a lot of things because it reminds me a little bit about the solar neutrino problem.
Oh, right.
Right. So this was an issue that when people were doing experiments on the ground in South Dakota, not too far away from here, a day's drive away, Raymond Davis, I believe it was even started in the 1970s, went through the 1980s. His experiment was collecting or detecting neutrinos coming from the sun. Mm-hmm. And today we know there are three different types of neutrinos. There is the electron neutrino, there is the tau neutrino, and the muon neutrino. And the experiment that was being run in South Dakota was sensitive to electron neutrinos. Okay. Now, we know that in the regular nuclear processes that occur inside of the sun, like the conversion of hydrogen into helium that ultimately releases energy, which we feel is the warmth and the heat coming from our sun, that's what powers it, nuclear fusion, there are a certain number of neutrinos that get emitted per second from the reactions that are responsible for creating the type of sun that we have in terms of its energy output.
Yep.
If you lower the reactions and lower the number of neutrinos, consequently, you also lower the amount of energy that's released from the sun to the point where it's not consistent with observation, with measurements that we make.
The sun isn't collapsing or expanding.
Yeah, and if you increase the reaction rate, so you increase the number of neutrinos that we should detect here on Earth, then that would increase the luminosity or the energy output of the sun, and that would be, again, inconsistent with what we actually measure.
Right.
And so the problem with the solar neutrinos was that we were measuring about 1/3 the number that we should be measuring. So we're missing 2/3 the number of neutrinos. Now, neutrinos are these particles that don't have electric charge, but we also thought they didn't have any mass.
Right.
And in the 1990s, other experiments, including the experiment in Japan, Super Econicati experiment, and the experiment in Canada, Sudbury, Ontario, the Solar Neutrino Observatory experiment, they measured the fact that neutrinos do have a little tiny bit of mass. So what happens at that point is that neutrinos can actually change flavors. They can go from being an electron neutrino to a muon neutrino to a tau neutrino and vice versa. So they can flip from one flavor to another or type to another because they have this little bit of mass. If they were massless, they couldn't do it as far as we understood neutrino physics at the time. So the resolution of this problem was that during the travel time of the neutrinos coming from the center of the sun before they reach the detector here on Earth, those electron neutrinos were oscillating into these other neutrino types. Yep. So by the time the neutrinos arrive on Earth, only 1/3 of them were still left as, or in being electron neutrinos. The other 2/3 were made up of the muon and the tau neutrinos.
And in fact, when they started testing for those other two types of neutrinos, the problem did indeed go away.
So now the reason why it was only detected 1/3 because they had switched flavors. And so that problem was solved. In fact, Raymond Davis won the Nobel Prize in Physics for running that experiment and discovering the solar neutrino problem. Now, before the resolution, before we knew neutrinos had mass, the solar neutrino problem, people proposed all kinds of stuff. They proposed the fact that, for example, they tried to adjust what was happening at the very center of our sun by somehow reducing the production of the neutrinos to only 1/3 the value of what we'd expect it to be. But of course, that runs into the problem that you then have the amount of energy being produced by the sun should be a lot lower than what we actually measure. Now, the interesting thing about neutrinos, if they are massless, and even if they have a little bit of mass, this is still the case, but especially if they're massless, when they are produced, they move out away from the sun almost immediately. There's no hesitation. They would travel at the speed of light, and they would take 8 1/3 minutes to make it here. Where the photons that we receive from the sun, they are created, that energy, in the core of the sun, but because there are constant absorbing and scattering process and emission process that are occurring, that energy takes a while to reach the surface of the sun. It could take upwards of 1 million years or so.
Right.
So the light coming off the sun really gives us a sort of a look at what's happening inside of the sun in the past, not the present day.
That's a good point.
Where the neutrinos tell us what's happening in the sun like 8 1/3 minutes ago.
Yeah.
And so it's an instantaneous measurement of what it's like in the core. So people suggested that something was going on in the core of the sun, at least some ideas that people had, that are affecting the production of neutrinos, that you have this sudden decrease in the production rate of energy, therefore decreasing the number of neutrinos now, but we won't know that for hundreds of thousands of years into the future when the light, all of a sudden, the light output decreases.
Right. Is that where the whole idea that the sun might host a black hole in its core came from?
That's other things. We won't get into that's
woo. I agree, but...
Yeah, that's way out there, no pun intended.
Yeah.
And so it's like this problem that you have, and you try to get into the basic physics of things and monkey around with physical constants and reaction rates and variables. But, there's a stubborn thing in physics and science, and this is called observations.
Right.
Right? You can monkey around with the equations and the production rate of energy, but at some point when they start running up against the observations,
They have to match what
Yeah,
we
they have
see.
exactly. Then we have to think of something else.
Yep.
And that's what we're really into now with the Hubble tension. You can add things, you can make things not consistent, the methods are not what as we expect, but you have to reproduce the observations.
Right.
Those keep in check the theorist, right?
And they are very annoyed at that sometimes.
Right. So as a theorist, you could do mucky around with the equations, right? You can throw things together, you can change this and change that and add that and add that. And then you can with a smile on your face, you come up with some idea, and then you go and look. Go to an observationalist, an observer in astronomy, and say, okay, do you see this? And they say, no, absolutely, that's not there. And like, oh man, and all this work was for naught, that kind of thing.
Right.
You have to keep theorists in check by making them look at the real universe and see if they match or not.
At the same time, you got to keep us observationalists in check, because we'll have a tendency of going out and just making observations and going, woo, look at all this neat stuff.
Right, you have to explain those observations. What do they mean in the grand scheme of things?
Wait, I have to explain them?
Yeah.
Oh, dear.
So that's how science works. Of course,
Right.
Those could be observations. In astronomy, they generally are, or in physics in general, would be experiments that people would do. It's the same kind of thing. So they go hand in hand. And then nowadays, you can even add in computer simulations.
Right.
A lot of that is done, especially in astronomy, right?
But-
Trying to simulate various systems and so on.
But in the end, it has to come back to match what you are observing.
Yeah.
And preferably, it can also make predictions about what you will observe. And when you get both,
Yeah. And so what's really interesting about this latest study is that the tendency was that all the studies that were done, except for the CMB type of measurement, like I said, there was a couple of exceptions, but they were really, rare in this sense, is all consistent with that higher value of the Hubble constant. This one is not. It's consistent with the lower expansion rate, the CMB.
right.
So right now, we don't know what's going on. Because you can use that thing that I mentioned, the hypothesis of this early dark energy idea, but that wouldn't affect these measurements of the time delay from the supernova.
Right.
It would only affect things that happen in the very early universe, the cosmic microwave background as an example. So now we have a new observation that really I think it really puts a constraint on this early dark energy extra component to the universe. Now we still have the dark energy, of course, but this additional a second dark energy that people tried to use. And that really puts a tight constraint on there to say, it's probably not going to be there.
I got it. Our universe spawned another universe through another Big Bang.
Well, the first thing I would say if I was looking at this is there's something wrong with this technique of the time delay from the supernova.
Right.
And then maybe the modeling of the mass distribution in the foreground galaxy cluster is too inaccurate to get a precise measurement. So really your uncertainties are a lot larger than what you think they are, and then therefore your value actually overlaps with both.
It would have really helped to have gotten that 1990s view of that so you could put it into the model.
Yeah, for sure. And if I'm not mistaken, I think Pat Kelly had mentioned several years ago when he was here giving his talk that part of this process of following up, obviously you can't go back in time to see the 1990 observation, but they made predictions going forward in the future.
Oh, excellent.
That his team was making these HST proposals to get time to follow up. And I don't think they were always successful on these proposals. And they're like, well, this is very important and it's only a one-time thing. So I'm not sure exactly where we are in the grand scheme of things, if there's more observations that need to be obtained in the next several years going forward, right? But that would be interesting if you can put a few more of these data points on this technique to really narrow down.
Because just a small variance in that time prediction could mean a huge difference in what they measure. So.
And the other thing is the modeling of the mass distribution of the foreground that does the lensing, right? The distortion of the space that the light passes through. If you talk to these various groups that do this modeling, they know they assume their modeling is within this precision or this uncertainty, and you wonder if those are
if those are
good or not, and you don't want to insult anybody, right? And it's a lot of hard work, obviously, but we have to look at everything,
right,
including their modeling. And so there's always going to be a question of how precise this modeling is done, and that doesn't mean just this in particular, this paper, but also other methods and techniques and results that came out in the last 20 years or so. There's a question mark on everything.
Right.
And a lot of the astronomers that are involved in this research are going back and looking at the very basic levels and trying to figure out if there's something that was missed. Right. And so, and it's like we talked about last day too, Occam's razor. You start with the simplest thing. Well, your technique, you underestimated the size of the uncertainties. They're actually much larger than what you thought they were. So start with your basic method, the very beginning of it, the ground level, and build it up and see if there's something that was obvious that we missed.
Right. And that's something that I've tried bringing up to people before too, is you've got to be prepared to defend your method, because holy cow, you can get shredded on that because, well, you didn't take this into account and so forth.
Right, and a lot of times, you hate to say it, but in science, anything we publish is peer-reviewed.
Mm-hmm.
And you'd wonder, I mean, if someone is publishing this large, detailed study that involved a lot of steps, how many of the referees, you see where I'm getting at here,
actually look through the steps,
go through every single step and reproduce the result of this study to see if it's right or not? In some sense, you almost have to rely on others that are doing almost the exact same work, that know or see something that maybe is wrong. And so as a journal, you seek out not just a random reviewer, you seek out people who are doing that same type of work. So they already know in detail of the science behind whatever technique or method the study is using.
And unfortunately, I'll bring up a point on that. Unfortunately, there are some areas that are so, I guess the word is esoteric.
Specialized would be
or specialized
a word, yeah.
That, there's only 3 people in the world that really know this material, and they're all 3 working on the same team.
Yeah, that's right. That's the other thing. And a lot of times, whether it's a criticism or not, I'll let you be the judge, but a lot of times, sometimes these big projects will bring in people. Mm-hmm. And next thing you know, the number of collaborators on this study is in the hundreds.
Right.
And that, brings you to your point exactly what you had suggested is, are we going overboard in this sense of this new trend in some sense, right? It's been going on for the last couple decades now, but certainly, if you go back in the 60s, the idea was there was 1, 2, or 3 people usually per team, right? And there were a lot of lone researchers out there that were publishing papers, and they were the only author. It was a single author paper. Right. Single author papers nowadays is like that is the rarity. Yeah, exactly, right? And it's not hard to do a search and look at the papers. What's normal now is to have many authors. In fact, or some of these literally is several pages.
Even 2 authors is getting kind of rare.
Yeah.
Usually it's like 3 to 7 is where I'm seeing kind of settling out. Except in astronomy papers where you're 100% correct. You'll have 20 authors on the paper.
Yeah, so you have these big collaborations, and you joke, I say, is the janitor on that paper too? I mean, where's all these people coming from? And you wonder how many even read the paper from start to finish.
Or how many did this one little section, and that's all they worried about.
Yeah, so in that sense, there's nobody to check those results, because everybody who would have the knowledge or expertise to check the results are part of the paper.
Yeah.
And that can be a real problem. So that that's one thing that we need to look at.
And it is one of those things. How do you deal with this? Because things are getting so complex that you can't just have one mind looking at it and working on it. It takes these collaborations to detail it, because we're getting where we're poking at things that are pretty well known, and we're just trying to tweak that last little bit out of it.
Yes, and you also wonder, not to get the political, but you also wonder when a scientist, let's say an astronomer, is proposing to use the James Webb Space Telescope or the Hubble Space Telescope, if they're the lone wolf, does that unconsciously provide a bias where you're not necessarily going to get a time because it's just you, where they're where they think you don't have the total expertise that you need to do that project, that really we're looking for multi-investigator type of teams.
Right.
Now, I don't know if that's an issue or not. The people who decide this maybe would argue against it, but I don't know for sure. It could be this unconscious bias that always appears.
It's entirely possible, but at the same time, we're all competing. What was it you told me? 10% of the proposals are funded?
Yes.
And with the costs that have increased, that means, if you had 1,000 proposals, anyway, only 4 or 5 are getting funded.
Right. So if you got like 30 proposals, you're looking at 3 being funded and maybe a fourth, and if you stretch it, maybe a fifth, but that's about it. But that doesn't mean that there's like 25 proposals that are trash that shouldn't have been even submitted in the first place and waste everybody's time. Maybe there's 1 or 2 like that, if that. But so you're looking at least, 20 proposals or more that deserved funding or deserved time on a telescope that don't get that.
Don't get it.
Now, several years ago, an argument was made, and it was made over many years, but the idea was you have like investigators that are on these proposals, you make a name for yourself. So you might see you're doing a review of a proposal, you recognize the name on as the lead, the PI, as we say, the principal investigator on the grant proposal or on the observing proposal, that this is somebody who's done a lot of great work. And there's this bias assuming that, well, this proposal that they're proposing now must be also part of this doing great work. So therefore they get a leg up in the competition. And there's always a competition. Right?
If this view is getting funded, it has to be a competition.
Yeah. So to get around that, a lot of the federal granting agencies now are doing these blind studies, if you like, reviewing process where you don't know who the investigator is.
Or even what institution
they're from or anything. And probably not even the number, right? Mm-hmm. Which means that takes away this bias of saying, oh, you're a lone wolf, therefore you're not going to get funding. We're looking at teams of people. Because if they can cut away all that information, so you're just looking at essentially the science justification of the proposal or the grant application, you're basing it on that first, rather than who it is. So it's not who you know, it's not who they are type of thing. It's what is the actual science. Is it worthy of funding? Is it worthy of getting time on telescopes?
Is your methodology sound? Is your question sound? Things like this. This is what goes into funding these proposals.
Now, this only started really recently in the last few years. Really, like a lot of the federal agencies and others are doing this type of method now. So it'll be probably a few more years going into the future to really get a large number of statistics that we can say for certain, how this has paid off. Has the awarding of observing time and grant money been more evenly distributed among the population of scientists than what it had presently? Did some big person always get funding and all of a sudden now is not getting funding?
Right.
Right? I mean, is that occurring? So these are some interesting things.
We're trying to correct problems that have cropped up.
That's right. And of course, there's a finite amount of money, so all these proposals can't get funded. That's the problem, right? They should get funding, but there's only, the apple's only so big. And, yes, this is the question the Wonder Group proposes. That apple is a finite size.
Right.
And when everybody gets their slice, there's still a lot of starving people left.
Right.
And they don't get a slice of the pie, you see?
And so the question becomes, do we slice it up thinner and not give everybody what they want? But here we can give you this much, try to find the rest somewhere else.
Or you join others who seem to be getting slices, and then now there's nobody to check your work.
Right.
Because the experts in the field now are all in the one slice.
Are all in one bucket.
And you run into that issue.
Yes. So
now, you could always, like I said, you can get into politics and always make the argument. Oh, by the way, the views expressed by Robert and I are not necessarily the views of the university nor the college and so on. There's my disclaimer.
Standard disclaimer.
Exactly. And so you can make the argument that look at the number of proposals we're getting in the federal agencies. There's clearly a lot more we should be funding. In fact, this is hurting our research and development. We could be much further ahead in the advancement of technology and whatever to improve life, around us, than what we otherwise would have been because we didn't put the money in it, the support that we need, right?
Because before we get into our closing, I want to point out one thing, and that is people say, well, what effect does that have on my life? And the answer is you don't know. When Maxwell and others were investigating electricity and magnetism at the beginning, it was a rich man's hobby. There was nothing to it. And Tesla and Edison took that information, that basic esoteric, who cares information, and turned it into a modern electrical grid. So you don't know what's going to prove to be worthwhile as far as affecting all of our lives. So keep that in mind.
Well, look what's in your back pocket.
Right.
A cell phone. Where do you think the cell phone came from? If we didn't support research in the science and technology like electronics And don't forget, the GPS system wouldn't work if it wasn't for the general and the special theory of relativity. So even fundamental science, fundamental physics that otherwise you would think doesn't really affect me in day to day, well, when you're on vacation trying to get somewhere you've never been before and you turn on your GPS system that usually is running through your cell phone.
Thank relativity and hence Einstein.
Thank the support of research and technology and basic science. We have to do it. If we don't do it, we get left behind.
Indeed.
Okay, so thank you for listening today to the podcast. If you're interested in STEM fields and physics in particular, please consider coming to the University of North Dakota, regardless of your age. We do have continuing studies.
Absolutely.
So if somebody is looking to change their career and midway through their life or something, I mean, there's ways to do that, of course, take on new challenges. One of the things I always like to do in my life, and hopefully others do it, is to keep learning.
Right.
Learn throughout.
I took a class this past semester myself. So
yeah. Now, our next podcast will be next Tuesday. That's May the 23rd at 3 p.m. Central Time. We always leave you with a quote.
Right.
Today's quote is from Galileo Galilei, and the quote is, "The increase of known truths stimulates the investigation, establishment, and growth of the arts, not their diminution or destruction."
So support the arts too.
Yes, everything goes hand in hand. It's a collected whole, not just, individuality here. Everything helps the whole thing.
Absolutely.
So thank you for watching and thank you for listening.
Y'all have a great time. We'll see you next week.